paper that okay, now.
Yeah,
Okay, so this is the paper that I read. I only had like 2 days to read it, so I'm going to do my best to give you the gist of it, but it might be a little vague in some points. Okay, so it's called a theory of local learning, the learning channel, and the optimality of backpropagation. Okay, so the basic idea is, say you have like a neural network or something similar, and you have like learning rules that are local and non-local. The whole idea is to investigate whether local learning rules can be as efficient or as backpropagation, for example. So the paper does a lot of legwork to make it more precise what they mean by local. A lot of people call it just a hidden rule in general and don't really elaborate on it. But the main idea is just locality. If a neuron can or a weight can only update itself based on its routing values on the connecting weights and nodes, that's local. If it has access to some kind of global information like the error signal, then it's not local anymore, right? So this is the thing. Okay, the basic now it's very important to note because they make this assumption. So this is a network structured in layers with a specific direction. It's important to mention because in physical learning system, it's very common to have like different topologies where you don't have like a predefined direction. It's just information flowing through the thing. But no, here it is actually just a traditional neural network structure. You have inputs and then layers and then output. And so the whole analysis is based on that. Right. Let me move this. Now let's go here. So right here they kind of defined a little bit what they mean by Sipon-Hibben rule, the Auger rule, this perceptron. So the learning rule, so that would be like the weight of between nodes. And the learning rule is how the weight is going to change. So a simple hidden rule is going to be just the product of it's going to be proportional to the product of the nodes values. So this is like neurons together. What was it? They bond better together. I don't remember what the phrase was. But basically, if you have like two neurons firing together, then the connection is going to be stronger. That's what this means. If they are not firing at the same time, then the connection is going to be weaker. Right, so it's completely local. So this weight only regards these two guys. There is no like error signal going on. And backpropagation. So this is the one where you actually have like something that's not local. It's an error that is being sent through the entire network. Right. Okay, so here we're just getting some terminology along the way. So here so this learning rule, right, we have delta Wij, which is going to be the function of some local variables. So they call O. So we can actually do this for every node in the system. We can write this equation for the node O. Its output. Actually, the output of the node O is going to be a function of a sum of the inputs that are multiplied by their weights, right? So here I drew a small diagram here. So that's basically it. Right, so this is why it's important to emphasize that this is for a directed feed-forward. I think it's called feed-forward network. Because information cannot go from here to here. It's just in this direction. All right. So by writing it this way, we can actually do a lot of stuff analytically with statistics. Let me go over this part here. Nothing. Okay, so they're just saying that the function can be linear or can be like a logistic function, a hyperbolic tangent. It's just an activation function. Okay, so we're going to talk about a little some the influence of some transformations of this thing, because what we're going to do is we're going to analyze these learning rules statistically to see if anything, if it's like a behavior, effective behavior emerges from them. So I
Can I
thought
ask
it
a
was interesting
question?
to mention.
Can I
Yeah,
just ask?
shoot.
So like local question, local I understand in the space of neurons, but do you also mean local in terms of time? Meaning, if I update my weights, can I use the knowledge of the previous states of the neuron, the previous?
That's a good question. They don't actually explicitly say that, but
Okay.
because they are actually doing like time averaging calculations on the learning rules, then yeah, it's going to show up there. Like this permutation of training examples actually.
Okay, so it
Touches
is
on that.
local only in the space of neurons,
It is, yeah.
but it doesn't have to be local in the space in time.
No, in fact, I think that's why they are doing this statistical analysis. It's because there is some information that gets
Okay,
sent through
that's good.
through
Yeah.
this. Right. So here they're going through the training examples. This is an example. Like what would happen if we permutated the examples, which is what
Uh-huh.
I'm doing in my spin glass system. So they're just going to assume that they're not going to be sensitive to the order they're presented because they're going to be very fast. But they don't mention if how much you expose to one example more than others is going to influence the system. But I assume it would. But yeah. But the thing is, so you can do these things. They're time sensitive, and I think it's going to like be baked in the effective learning rule when you average over time. So okay, so they're just going through some more examples here of hidden rule or Hopfield, like functional forms. Okay, so the paper is going to just focus on polynomial functions. So that's their focus here. And they also
Polynomial in O's and W's, right?
in O's and W's, yeah.
And what is
And the T, which T is like the what do they call it? It's the non-local stuff.
okay?
Some kind. I don't know if it's the error or target. Oh, it's target. It's
Uh-huh.
target.
Okay.
So it's the non-local stuff.
Uh-huh.
Right. So this would be a local learning rule, and this is not a local learning.
Uh-huh.
I mean, it is local. It's supervised, they call it, but it can be local, I guess. Something stuck with it. All right. So what did I write here? All right. So this is they're talking about the degree of the polynomial that they're willing to consider. So the degree would be in the on the weights specifically. So not on the other things, just on the weight. The polynomial is just on the weights. But you asked me this question, I think I said it wrong.
Uh-huh.
So when you look at like this learning rule, for example, so we have only one weight, so this should be like degree 1, but because we have like some other node here squared, and we can actually represent it as a summation of its own, incoming spins and weights, then the actual degree of this learning rule is 3, because it's going to show up 2 more times inside this area. But yeah, this is where I actually start to have some questions, because if you're going to do some averaging through time, then one would think that this is, well, I don't know, because this is like layered feed-forward architecture, so maybe it is 3. I don't think it, but if you have like it can go in any direction, then I think it would actually start to show up in a more non-trivial way. It would be difficult to qualify, define the degree. Anyway, So we have some terminology here. It's just very defining what hidden means in this context.
Oh,
So
it's certainly going to be of high degree effectively as you do time averaging. Maybe that's what you're
yeah,
saying.
yeah,
No, but
but they
it does,
assume this degree in order to calculate the
it doesn't matter, right? So this is the simplest assumption you take. Yeah, that makes sense.
right, yeah. Right. So time scales and averaging. So this is the bread and butter of the thing. So we're going to rewrite the learning rate like this, and this can be like the learning rule as this thing, and then sorry, that's not what I meant. They're going to write the new learning as this kind of equation. So this is the learning rule, and this is going to be like a learning rate. It's just a way to get parameterize how much you want to change the copies, the connections. Roadmap. Let's keep that. So in the linear case, parameter. Let me go to my notes here. Okay, so it's a feed-forward linear network, and we're going to focus the analysis on specific nodes, right? As I said before. And functional forms that are polynomial specifically. So, right, so the learning rule is going to be a function of t, the specific node, and the inputs and the weights of the inputs with it. And so this is the expectation of all possible terms using of these functions here that they can go there, right? So these are the exponents in t, in o, in I, in w, and we can actually expand this and calculate analytically most of it. So all possible terms, that's what they want to do. Yeah, right.
Sorry, there's still one thing I'm missing. So, uh,
Sure.
do they have a global learning rule like for this feed-forward network, and yet they're trying to see whether you can learn that rule a global loss function, not rule, a loss function, whether you can learn it by adjusting, by calculating some local quantities and then adjusting your weights according to those local quantities. So that's one
No,
possibility. Or they just say, no, 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 we will define our loss function locally. And if we define it locally, then obviously there is no need for back. You can still do back propagation, but there's no to the leading order. You can just adjust your weights by finding the gradients with respect to the local loss. So I'm
it,
just still not understanding what is the learning is it a global loss function or is it a local loss function?
it's probably a global loss function. They don't actually mention it explicitly, but the idea is to solve like, global problems to the network.
Okay,
They don't use the term loss anywhere that I saw.
I mean this E that you have here, some model of loss function, I guess.
Oh, E is the input, right?
No,
Input to the specific node.
not I, but E.
Sorry, Portuguese is
Yeah, I know. Russian the same. No, no, E. E
yeah,
is
okay.
something that has to do with the loss function, something that you will use to adjust your weights. But again, there's two things. Either you can just define the loss function as some function of E, and then you know how to adjust it, or you don't, and then you like trying to model this E, find what it is.
This E is the expectation value, and these are just all the possible combination of terms. This is for the learning rule specifically. I don't know if that's what you're asking.
Well, when you had a learning rule, there was E there in the like gradient descent like equation what you had above. I mean, if you can scroll up, I'll show you where this equation is.
Up? Yeah.
Up, yeah, yeah. But this is it, right? So 16. I thought E was No, it's expectation taken. Well, I don't know.
Expectation taking over the corresponding epoch. Yeah.
Oh, okay. So E is expectation. All right, fine. So, but delta W is somehow has to be calculated by minimizing loss, and that's loss is either defined locally, and then there's a
Right.
local.
But I mean, this is the learning rule, right? So it's either local or it's going to be
No, that's not the
the
rule yet. This is just, yeah. So the rule is 14. So it's saying that it's proportional. For
yeah, it's
example,
proportional to this. Yeah.
yeah, so or something else. But is this how you define your learning? Or this is how you model your learning? So this is what I'm not quite understanding. So you can define like, okay, maybe 12 will answer that question. Well, no. See, those are all 12, 13, 14 are just proposed models for what your local loss function would look like. Okay, well, anyways, I think there's still this two possibilities. Do you want to define your loss function locally and then it's a local learning by definition, or you define a globally loss function and then you just trying to model what would be the right proxy for the global loss function but defined locally. For example, like locally you can calculate entropy and say, okay, I want to minimize entropy, and then for neuron, and then it may or may not correlate with the global loss function. Okay, I'm just
Yeah, I don't know actually. That's
all right. Go
not,
ahead.
not sure.
Sorry.
All right.
May I ask you a question?
Sure.
Sure.
If you go back to page number 5, example 4, the Hopfield network. Yes, here. Yes, example 4.
Yes.
Example 4.
So example 4. Where is example 4? Oh, there we go.
So here this energy half so this they're not minimizing this sort of an energy.
Yeah,
They
so
defined
in this case, I think this E is the loss function, and they will be minimizing energy. I agree with you. Yeah, and then it
Here
will
it is.
yeah, and then it would
it's
be
not,
local, right? Definition.
okay. So that's different from what you're defining later on. I mean,
Yeah,
I'm not
this E and other E is E is the energy, which probably
Yeah.
related to loss, and the other E is just expectation value. I got it wrong. So now makes sense.
Yeah, not only that, this is like a general, this is not a specific quantity. It's a stand-in for all possible values that
No,
could
I
actually enter
understand.
here, right?
Yeah,
So
it's just a
this could
function.
actually be a linear combination of a bunch of different
Yeah,
terms, square in t,
yeah,
cubic,
yeah.
or whatever. And this is just saying, look, we can calculate all the possible combinations of these things, the expectation value.
but they're somewhere using that example 4 and studying it using this local study or not.
Directly, no, I don't think so. Also,
Okay.
I
I'm
think
still
all
a
of
little.
them are local loss functions. So now I don't think they are answering that question of whether you can define a local loss to effectively learn a global loss. So they're not discussing this duality, local global. They are mostly concentrating in, okay, the learning rule is local. Let's see how you can use it to learn anything at all.
Okay. Thank you.
And energy
So,
is usually local, so
right, yeah. Okay, so they just go through a few examples of these terms and whatever. Okay, so they build a tables of all possibilities of the constant, and then they have the expectation. But there are terms that like this one is simple hidden, right? And you got because that or this. Right. So that's that means that we can actually do statistics analytically. That's the whole thing they're trying to do. So here's these more tables. Okay, so the hidden rule for the supervised simple rule is that the weights diverge. That's the main result that analytical they got from this, which is also my experience, by the way. they do just explode, but they at least got some equation that actually shows that.
Well, hold on. The weights will diverge depending of what kind of loss function you have. I mean, if it is linear, so this dw was linearly proportional to w, then its potential is effectively like quadratic, so you can stabilize it. So I think it just depends on what kind of terms you add to your local loss function, and then you can always stabilize it by adding.
Where would the loss functions show up here? Because I think they're interchangeable, like the
Well,
loss or
yeah.
the learning rule, right?
Well, I mean, learning rule or dw equals.
You were muted now. Hello?
Can you hear me now?
Yeah, can you?
Yeah, okay. So no, I think the learning rule is what you get, like, and the loss function are two sides of the same coin. You basically the dw equals to something, and that something is just a gradient of the effectively loss function.
Right. Yeah, exactly. But they're skipping that part. They're dealing directly with the learning rule.
Right. So, but basically what will happen, you will just get one more power of w's there. So if you had a linear w in your learning rule, then you have to actually put quadratic there, and then it will be stable if the coefficient in front of it is positive, whatever, one or the other, and be unstable in the other case. So since you put a term that you put was something like wij oioj, okay, and then depending of what oi or j's are, this may or may not be stable, and so I see easily how it will be unstable, because
right.
if
But they call simple hidden rule specifically when you don't have these other terms. But there are, like, even in this table you can actually see the square term, like here. I don't know if this is exactly the one we're talking about.
but this one is definitely unstable, because this one, again, you add one more power, it becomes a cubic.
I think this is the one with the like
this may or may not be
something.
stable depending of the expectation value. So I think all this should be analyzed, and you know it better than I do, in terms of this effective theory, when you just average over all the O's and I's, and then see how the W effective potential for W behaves, like something like effective field theory, but for discrete variables. And so the instability of W's, I think, can be very well understood, and it will depend on
yeah. No, they even show, like, I think the one with I think this is the one where we're talking, right?
Yeah. Right, exactly. So W square, of course, corresponds to the potential, which is W cubed, and that W cube is unbounded from below. So
let me see if there's a plot. I think I remember a plot for here. No, this is the simple hidden. They just goes to infinity. They didn't plot the other one, but I think they do mention that this one is actually stable or something like that.
Which one is stable?
I think it's Poja or this one here.
Oh, it is stable. That's strange.
When you get this guy, well, it's not. It doesn't go to infinity. That's what they call stable. But I don't remember if this is.
Well, it may be stable, but it depends on eta and mu.
Right.
Cubic functions can have local minima, and you can get yourself stabilized there. But in general, it would be unstable from below.
Figure 5.2.
Okay, good.
Oh, it's all the way ahead. 5.2. Okay, that's it. So see, it doesn't go to infinity. It has like a asymptote. Hikati.
Mm-hmm.
All right. Right. So these are we started with just degree 1 or smaller than 1. But for degrees, where was I? Ah, there we go. So for degrees bigger than 2 or equal to 2, and then it's now no longer solvable analytically. So except for a few specific cases, like for the Riccati, which we just saw, but they are not going to look at them too much because the whole point of the paper is doing things analytically. Yeah, right. But anyway, let me see what's the next important bit. Section 4. Okay, so section 4. Okay, so now we're going to actually analyze learning in the long linear case. So they have two main assumptions, simplifications that they use because they need the simplification, otherwise we can't actually solve analytically. One of them is this one, which is similar to the dropout approximation, which so basically you replace the output of a neuron with the expected input value of the input, something like that. And the other assumption is here that the OIs are almost independent from each other, which is a pretty strong assumption, I think, but I guess to be able to analyze analytically something, you have to do something about it. All right. But they do have like simulations later that like justify some of these things, and they show that it actually makes sense. We already talked about this guy here. So the Higgs rule goes to infinity, and we saw the other. So this section, I didn't dive too much into it. So they're basically saying that the whole machinery that they built, all the tables, all the way to calculate new things, is also a generative tool. Like they can use it to generate new learning rules. They have specific properties. Now 6 is where they actually do a bunch of interesting stuff. Basically, so the first thing they do simulations on Boolean functions. So they have like here 2 inputs. So this is basically every possible combination of Boolean functions. You know, it's not just like and XOR, so just every possible combination. And they all work, even with the local function. So that's good. The fan-in is just number of inputs to each node, right? This is the new terminology for me, but apparently it's very common for this type of stuff. Anyway, so this is the promising aspect of it, that hey, it does work. Local rules, they learn simple Boolean functions. But so the gist of it is that later they're going to show that when you scale up, they stop working. Like if I have like 200 inputs, then it's not going to work. And they show that it's not fundamental. I mean, it's not a matter of finding the right tuning. It's a fundamental issue. But yeah, this is the part where it's going to get a little vague. It also gets extremely dense. Like they have this theorem here. Let me see if I can find my notes on this theorem. Okay, so here's just, this is not the theorem that I want to talk about. This is just showing that the Higgs rule has this specific form when you calculate the expectation. Right. Limitation of shallow. Okay, yeah, there we go. So yeah, so they try to learn the image work using purely local learning, and they all fail. And they do go ahead and prove why they do fail, but that proof really just I could not get into it exactly. But they do. But the caveat is that they have a lot of assumptions there, so I'm not entirely sure about their proof. Yeah, that differential for a function. Right. So okay. So limitation of deep local learning. Yeah. So this is what they're saying, that it's not going to work. And here they are actually talking about alternatives. So they talk about this is the learning channel that appears in the title there. So the learning channel means that you have to actually send the signal back in some kind of way. They have a theorem here that proves, where is it? Like deep targets. Deep targets basically means that, like in my case where I have like spin glass, instead of putting just the inputs and outputs with external fields, I would actually do external fields on each of the nodes to actually push it to be in the right configuration. That's basically what it means to do deep targets. You're actually directly manipulating every layer of the structure. Now they do prove here something, but the learning channel. The learning channel, they prove somewhere that I completely lost now, that it's actually equivalent to backpropagation. And so it's sending the information somehow. It's like every node is going to save like the error and it's going to push forward the error and do its thing.
Okay, so maybe that answers my question. So you're saying that if you had some global loss function or boundary loss function, and then you're trying to understand what terms in the local learning room would they correspond to if you did do the backpropagation, then there's an answer to that. So there is a specific term you can add to the.
Yeah, would be that. I'm not sure I understand the question, but the idea is that
Well, you have a boundary loss, and you do usually have loss function like a mean squared error, and then you can use backpropagation to adjust weights everywhere in the bulk, and then in the neural network you can go through all the backpropagation steps and adjust every single weight there. Okay, but then you may study to what kind of local learning rules does that correspond, and then perhaps you can derive what are those local rules should be effective.
I think what they mean is something like this. So imagine you have like some nodes here, 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 here. So the idea is that like, oh, so this weight is only going to update itself based on these guys here, right? And the other weights as well. But they're saying, so if there's like a main error calculated globally, then this guy's not gonna know about it. Unless you had some way of putting the error next to it, side by side. Like there was a
Well, no, that's not global. Doesn't answer the question on the backpropagation. So the backpropagation.
not on the backpropagation, on the learning channel. The learning channel is the strategy we were talking about.
Okay, so then it does not answer my question. Okay, good.
Yes. So yeah, I think this is actually similar to the thing we saw a while ago. What was it called? A contrastive Hebbian, they called it, where they had like two identical networks, one side by side, and they connected them on specific nodes. Because that was, I think that was supposed to play this learning channel role, because then each node would know, okay, so I'm actually far from the actual ideal by this amount. Oh, I'm far from the one I want from this amount. So it's still local in the sense, but I mean, physically, it's very difficult to build something that does that, but that's the idea. Meanwhile, backpropagation is equivalent to, what was this, deep learning? No, deep learning, no, not deep learning channel, what was it called? Deep targets, which I didn't get time to actually understand exactly what they mean. But okay, so yeah, I think this is the edge of my understanding of this of this paper. If you guys have any questions or let's see if they have some interesting stuff back there. No, just appendix. All right. That's basically.
All right, perfect. Let's see if there are any questions, comments.
Yeah, my specific question is how applicable this is to different architectures where you don't have like a layered and specific direction. What the topology has,
No, I think
what
what
role
would
does it
be
play?
what would be useful is to actually have a map or an understanding of how the back propagation, to what kind of learning rules the back propagation step corresponds. I think that would be useful.
Yeah, they actually have a theorem proving this. I could not find it because it was buried at the middle of it, but it is like equivalent to deep targets. So it's not a local rule. It's a middle ground between local and global.
All right.
So apparently cannot be. It can't come from purely local. It has to get something else. At least under these assumptions of one directional layered approach. I don't know what happens when you have an actual physical system where a signal doesn't have a preferred direction. But I think the main idea is actually very usable, even non-analytically. Like just like I'm doing effective calculation of the energy of the system of the Hamiltonian, but I could actually be applying to the learning rule as well to see what it looks like, to see if there's any global information being encoded in the learning rule. That would be interesting.
Perfect. Right. Are there any questions? All right. Thank you, Diego.
All right. Thank you.